Okay, so I think that's enough people. Okay, let's start then. So, as you can see from my screen, we have a zombie apocalypse, and a scroll was found from someone named Equivalue with a request for help. Okay, one second. Some more people are joining. Let me just allow them in. Yeah. So this scroll was sent out by Equivalue. Just one second. Let me check if recording has started. Uh, just one second. Let me check if recording has started. Okay, cool. So yeah. So this was the scroll which was found. And luckily, this entire monstrosity of a code was decoded. And the initial part said that Equivalue is stuck in the land of the dragons. And if he is not saved inside the next week, the zombie apocalypse will spread further and further and eventually take over everything. Well, as we begin to decipher this, we can see that there is a lot of jumbled lines, repetitive. It is not quite clear how we can find the space to reach equivalue. So we use one of our best friends, graphs. We see that this entire question is based on how we can move from one place to another. This is a standard place where graph problems can be used. So before we dive into this, let's go over graphs. So let me just share my screen again. Yeah, I hope the example was nice. Okay, so beginning with graphs. So graphs is something which may seem like a complicated data structure, but in its very core, it is quite a simple concept. A graph is two sets. One set is the edges, and the other set is the vertices. So anything which are like places, buildings, towns, all of these come under vertices, and anything which we term as paths come as edges. So if you have a structure like this, where A points to B points to C points to D, and say you have E and B points to E, then this is a very simple graph. And the way you would write it as two sets is that G, which is the graph, is equal to the set containing two sets, V and E, which we said here E and V. And then V would equal A, B, C, D, E. And E would equal to each of these edges, A to B, B to C, C to D, and B to E. So the way we write it is usually as tuples, or this could itself be a set, but usually tuples are preferred for maintaining order. So now that I bring the term order, just before that, did everyone understand what the basic structure of a graph is? A graph is the two sets and the relation between all the vertices and how they're connected via edges. So I hope that made sense to everybody. If not, you can unmute or just write in the chat, whichever you're comfortable with. Okay, so I will assume that that made sense. Moving on, I'll be explaining the concept of directed versus undirected graphs. So this is a quite simple but powerful concept. What it says is that if you notice here, there was this arrow from A to B. If you notice, all the edges, they were arrowed. This is showing that the only possible path, if we think of this as, say, a city, is that I can move from A to B, but I cannot move from B to A. This is possible, but this is not possible. It just shows direction. So if you have A to B with no arrows written at all, then this implies that A to B is possible and B to A is possible. It just means it's bidirectional, or you can say there is no direction at all, undirected. They both are equivalent. So undirected is equivalent to bidirectional. So now I think you will be able to see why I said that we usually write them as tuples, because order matters. Clearly, if we had a directed graph, A to B is not the same as B to A, right? I'm pretty sure this is clear. So we can say that graphs are of two types. You can either have directed graphs or you can have undirected graphs. Note, an undirected graph is the same as a directed graph where every edge is bidirectional. So I'll just give an example for that. If here we converted this graph slightly such that it's A bidirectional B, B bidirectional E, C bidirectional D, then this is the same as just having A to B to E to C to D. You can have no direction on the edges and it will be the same as having edges in both directions. So I hope that directed versus undirected graphs make sense. So here I'm just explaining the core theoretical concepts. The usage of all this will come further as we move on. But theoretically, does directed versus undirected graphs make sense? Okay, awesome. So why all this talk about graphs? What makes graphs important? Well, one of the core usages of graphs, is there a question? Okay. One of the core usages of graphs is traversals. So suppose we take the previous example of the zombie apocalypse, where you have towns and you have roads. Each road signifies that you can move from town I to say some town J. So here you would see that the towns can be represented as vertices and the roads are edges. So how graphs help us is, suppose you wanted to find the shortest path from some town T1 to some town T5, and you have loads of crisscrossing paths. Suppose you can go from T1 to T2 to T3 to T5, or you can go from T1 to T4 to T5, or you can go from T1 to T3 to T4 to T5. In a city, you would have multiple possible roads to reach from one place to another, a general understanding of a city. In situations like this, something called graph traversals helps us a lot. The word traversal basically means movement. And the reason we use the word traversal is that certain algorithms, which we will be covering soon, show us how we can move from one vertex to another optimally. When I say optimally, there are many different meanings of the word optimal, because there are different ways I might want to reach one place to another. I might want to move the shortest distance or the shortest time. There are many different ways in which optimum can be defined, but we can say the usage of graphs for this specific scenario is that it allows us some optimal movement from a town to another. So is everything so far clear? Because I'll now be starting with graph traversal algorithms. Okay, I think everything is clear. If you have any doubts at all, feel free to unmute or send it in the chat. Okay, then let's start with breadth first search. This is the first algorithm which we'll be covering today. It is called breadth first search, or BFS, which is a shortened version of that. So suppose we have this rather intimidating looking graph which has a lot of vertices and a lot of edges. So as you can see, just to explain, we can say that G is equal to V comma E, the vertices and the edges, where V is equal to A, B, C, etc. I think up to Z, but all the letters are not there because I don't know the letters in order, which is kind of sad. Then we have the edges, which here are undirected. So suppose this edge shows that I can move from A to Y and from Y to V. That's what it means, just as a recap. I have edges of the form, say, A to S, S to B, etc., etc. All the edges of this graph would together form the set E, all the vertices together form the set V, and together the two of them form G. So this is how you would define this diagrammatic graph in the form of sets. So moving on, before I formally define what BFS is, I feel like it is much more helpful to intuitively understand how BFS works, which is why I'm explaining it with the help of an example. So suppose we are, let's choose a different color. Okay. Suppose we are here, we are at S. And we want to know which vertices can I visit from S. So this might sound a bit vague, so I will define what the term visit means. So what I mean by visit is if you follow any set of edges, you will begin at some vertex and you will end at some vertex and you will cross a set of vertices. So each of these vertices which you reached are the vertices that you visited. For example, if I go from S to D to X, or maybe from S to B to C to Z, then all of these vertices are the ones that I visited. Note, it is impossible to reach, say, G from S. There is no path at all from S to G. I hope that's clear. So intuitively, what would we do? Let's say we have S, which I'm going to draw here. I say, okay, I can go from S to A, or I can go from S to B, or I can go from S to D. So let me just draw out all three cases: S to A, S to D, S to B. Now you say, okay, I can reach these three. Let me move on further. Where else can I go? So if I am a D, I say, okay, I can go to X, I can go to C. But if I go to X, so let me just write this much. From S, I can go to D. From there, I can go to X. Here, what we would intuitively think is, let me add this. From X, I can go to C. This is not what BFS does. What BFS does is, wait, I can go from D to X, that's cool. But there are still these two vertices which I have not checked. What about B and what about A? So what BFS does is, it says, okay, I can go from D to X. Now let me wait. I have found one path forward from D. Now let's go back. I was at D, but why did I reach D? Because I was checking what are the neighbors of S. So B and A, we still have to explore those. So from A, I can go to Y, and from B, I can go to C. Now we say, okay, all good. We have checked A, we have checked D, we have checked B. Now we can move on to the next layer. The way it will check the next layer is that it will go, okay, X. It can choose any of these three, by the way. I'm just, for some reason, choosing X. So it goes to X. It says, okay, there are no edges outside. There's nowhere else I can go. But I can go back to D. But it says, okay, D is already something I visited. So that's not going to help me find a new place. So X is done. We can say that it's done. It won't, this is not saying that something else is there after it. So let me maybe say done. So now it says C and B are still open though. From C, I can go to Z. and then from Y there's I'm done. So this layer is done. Then I move to Z. I say, okay, there's nothing else I can do. So I'm done. These are all the vertices which can be visited from S. And if you look at it now, naturally you see, okay, this entire thing, okay, that's a bad one. Yeah, this entire thing is all the vertices I can reach. I would not be able to cover E, G, F, or W, which is exactly what this tree structure says. We call this a BFS tree, but that's just terminology. But intuitively, did we understand what BFS does? What BFS does is it checks breadth. It checks all the possible neighbors at some level before moving on to the next level. That is why it's called breadth first search. So instead of giving the pseudocode, I will now explain DFS in contrast with BFS and then explain the pseudocode of both simultaneously so it's easier to understand. Oh, yeah, you have a question? Go on.
Yeah. What won't BFS also check that there is an edge between D and C?
Okay, so you are saying that at some point we had S to A, D, and B. Then from D we went to X. Then, yeah, from D we went to X. And then we have to cover the breadth, right? So let me just erase this. From D we went to X. And then we have to cover breadth. So instead of checking D, we check B and A first. And B will cover C already. In the case where suppose B was linked with Z, and we had B to Z written here, and then A to Y, then D to C would still be open or unvisited. And then, wait, sorry, 1 second. I think I made a, yeah, sorry. I made a slight mistake. Oh, okay, sorry. Yeah. That is a very good point. I am so sorry. Yeah, that is a very good point. I did make a mistake. Yes. Yeah, what Naveen is saying is exactly right. I made a mistake. I did not see this. Sorry. You are right. That is a good catch. From D, I will be able to visit everything in the neighborhood of D, which is X and C. Absolutely correct. Sorry, that was my mistake. You can check everything in the neighborhood. But as Naveen is pointing out, this gives us a very important understanding. There can be multiple BFS trees which are all correct. So the BFS tree which I drew, this is not wrong. It's just because this is a valid iteration of how BFS would work. The only thing is what Jayaditya, I think, was saying is also valid. Because as I was explaining, when I was going through this layer, I could have chosen these vertices in any order. And depending on the order in which I chose the vertices, the rest of the vertices would form the tree. So there are multiple possible trees which are correct. In case this is a bit confusing, I will give a quick example to explain this. That's a very good point which was brought up. So just I'll okay. Just someone else joined. Yeah. So there are many multiple BFS trees which are possible for the same graph. So let me just I have an example for this. Just give me a second. So, I mean, this same example itself would work because, yeah, if you look at C, it can be visited in two ways. It can be visited from S to B to C, or it can be visited from S to D to C. So, deciding how you will reach C will give you two different BFS trees. But both of these will be correct BFS trees. It depends on how you implement your BFS that which tree you will get. But all of these multiple trees would be quote unquote valid. So I hope this didn't cause any confusion. Is BFS clear? Just intuitively, how it checks by breadth. Is that clear? Okay, cool. So now let me explain DFS, or depth first search. Both of these are on a intuitive level. So depth first search, as this is called, okay, that's bad handwriting. Depth first search and breadth first search. So maybe some of you will be able to guess from the name itself that while breadth first search checked everything, all of its neighbors at once, this checks neighbors at once. Depth first search does something contrary to this, where it goes as deep as possible into, it does not check all of its neighbors, but goes down the subtree, if I may say that. So that might sound complicated. So let me just give this example. And CFC. Okay. So this would be an example where BFS and DFS would function differently. So again, if I start from S, what BFS would give me was, it would say S, then I have three possibilities, A, B, and C. But what DFS says is, okay, I have S, then I have A. Now, let me just, what would seem intuitive to us is, let me just check as much as I can with A. So from A, I can go to X, from X, I can go to Y. And then now that A is complete, let me go to B. Okay, B has nothing else. Let me move on to C. And that would be how its DFS works out. Note that, okay, sorry. Note that for BFS2, in this scenario, you get the exact same tree, but the way in which you get it is kind of different. Because here you go S to A to X to Y and then B and C, while here you go S to A, B, C and then X, Y. So that's on an intuitive level, the difference between BFS and DFS. One is that it checks breadth and the other checks depth. Okay, that's take a graph with cycle into DFS. Yeah, that's a good idea. I was thinking of first giving the pseudocode for both and then showing the example so that it makes more sense. Yeah, cool. So, just a second. Yeah. So DFS on a graph G, what we basically do is that, okay, so it will be on a graph G with a source. Right, because here as well, we chose that we start from S. So because we are starting with, so mentioning which vertex we start the DFS traversal from is an important thing. If we said A, then we would have a different tree. So DFS on a graph, and we have a source. So what it will do is that, as we explained, it will check something called the neighborhood. Okay. I should probably explain something before this, my bad. So how exactly are graphs stored? We spoke a lot about what graphs are, but how exactly are they stored? Yeah, I should have added this before. Yeah. So storage of graphs. Because if you're thinking of implementing any of these algorithms, you can't just have something like this stored in your computer or your program as it is. So what we end up using is one of two things: adjacency lists or adjacency matrices. I'll go over these quickly because it's just more of an implementation detail, but still something nice to know. So what adjacency list does is, you have a huge list and you have each of the nodes, say A, B, C, D, and it basically shows which all nodes it has a direct path to. So suppose you have A to B to C. This guy would have B, he would have C. This would be how the adjacency graph is. And then if you have B back to A, then this would be C, comma A. So adjacency list is quite plainly for every node, which other nodes, nodes and vertices can be used interchangeably, by the way. For every node, which other nodes does it have an edge to? That would be a part of its list. So this seems like quite a nice way to store your graph. But I will give another way in which graphs can be stored as well. Also, let me ask this as a question. From the name adjacency matrix, does anyone think of a nice way in which I could store this graph? Let me give a bit of a hint by drawing out what the matrix looks like. Exactly, zeros and ones. Do you want to explain it by what you mean by zeros and ones? Your answer is right. Exactly. So if a comma, yeah, as Akshat and Advik said, yeah, adjacency of a comma b is equal to whether a and b are connected by an edge. Yeah, very well said. Or even the previous explanation is completely fine. So when you say if a is adjacent to b, it means if a and b share an edge. So if you had a to b, then let's just keep it unidirectional for now to make it slightly simpler. If you have a to b, then this would be 1 and this would be 1. So what it's saying is, if you have any I comma j which are connected by an edge, then aij is equal to 1, which means it has an edge, and aji is equal to 1. This is the case where it's undirected. So 1 basically means edge exists, and 0 means no edge here. Now, I have a question here. What do you think in general? This question might sound vague. Which do you think is quote unquote better, adjacency list or adjacency matrix? This might sound like a vague question. So I'm interested in what people think. What do you think is better, adjacency list or adjacency matrix? Okay. So mixed answer says adjacency matrix list. Yeah, as Advik is saying, depends is a very important word here. Both of these are valid ways to store a graph. There's nothing wrong with either of them. I can use an adjacency list or I can use an adjacency matrix. But the use case of when I use list and when I use matrix is quite different. So I'm going to throw two new terms. This is a bit unnecessary, but it's a fun thing. So I'm just going to add it. Dense graphs and sparse graphs. Just from the way the names are written, sparse graph means that the graph is quite spread up. It's spread out. You have a large number of vertices, but the edges might be few in number. While dense graph means it's compact. There's a lot of vertices, there's a lot of edges. Everything is quite close together. In both of these cases, which do you think would be better, matrix or list? You can answer in the chat. Okay, I have an answer. Uh, okay, that's an interesting answer. And do you want to explain your answer?
Okay, so in a sparse graph, then where the degree will be very low, then just checking whether two things are adjacent in a list itself will take the the size of the degree itself, which will be low. So while finding the neighbors of something will be very fast compared to an adjacency matrix, but in a dense graph, finding the things in a list itself, finding the neighbors will not be that much faster than finding it with the matrix. And finding of whether two things are neighbors are much faster.
Exactly. I couldn't have said that better. Did that answer make sense to everybody? Or should I maybe try to explain it in a different way if it did not make sense to someone? Okay, then that's exactly right. So this was just a side note that you have two different types of ways in which you can store a graph, and both of them are equally correct. But in different use cases, you have different ways in which you can store the graph. But as someone had written, generally we do use adjacency list, but adjacency matrix is also used in some cases. So moving back to pseudocodes of BFS, DFS. Okay. Okay. So we define DFS on a graph with a source as follows. So I'm going to write the pseudocode quickly, so that will give everyone some time to go over it, and then we can discuss the pseudocode. So what we say is mark. I'm going to write source as S just for the simplicity of writing this easier. So mark S as visited. Check. Okay, for each neighbor in S, N in S, N as visited. So this is a nice recursive method in which we can do DFS. Does this make sense? Intuitively, what we are saying is, if you're at some vertex, you mark it as visited, and you check its neighborhood, which means if we have an adjacency list, then you check all the neighbors in that adjacency list. For each of these, you just recurse. You go back and you start from here. So does the concept of recursion make sense, or should I go over that briefly? Yeah, as Harleen said, you can do that. That's definitely true. But here I'm just trying to explain in a simplistic manner how DFS works. If you did try to code that, yeah, you're absolutely right. You would add that. So you can just check that. Yeah, exactly. You do have to check whether N is visited or not, as Harleen was saying, because otherwise you can just run in an infinite loop. If you go like this, and then like this, and then just you keep repeating, it could be an infinite loop. So that's right. You have to check here that, okay, let me just add it because it is a pretty important point. So if N is not visited, then you do all this, else just continue, right? You move on. That would be a more correct way of writing this. Absolutely. So from this, I'm pretty sure you can see how we would write BFS as well. Does anyone want to take a shot at saying the pseudocode of BFS? Just the basic structure. You can unmute and say it if you want. Yeah, exactly. We'd use a data structure called a queue. But since I don't want to add any new data structures and make it more complicated. I will give a more sort of hand wavy explanation of how BFS works. A queue is the appropriate data structure, and in the notes, I will put it with queue. But just in case someone does not know how the queue structure works, I'll not be going over it in that way. So for BFS, what you would do is you would start at your source, and then here you would say cover all neighbors of the source. Again, here as well, you would have to check that it's not been visited. It's not been visited prior, but you cover all the neighbors of the source, and then you take one of them and then you recurse. That's the basic idea of how BFS works. The implementation details do require queue, and I'll be providing that in the notes, but this is the theoretical understanding of how both BFS and DFS work. So BFS and DFS here have been explained with recursion. So far, are there any doubts at all? Yeah, as chess coder is saying, queue is quite useful, so you should know this data structure. But in case you don't, I hope that you've at least theoretically understood how BFS works. For implementation, you definitely need queue. It is an important data structure to go over. Okay, so then maybe we can do a couple of examples. So I'll just wait for a minute. So if there are any doubts, you can let it sink in perhaps, and then we can continue. Okay, so I'll just assume that everyone's understood, which is great. So moving on to problems in both BFS and DFS, I'll start with defining something called a cycle, which is another definition which we should cover. So a cycle is just what it sounds like in very plain terms. It is a loop in normal term. So you have something which goes from A to B to C to D and then back to A. This is a cycle because you can go from A to B to C to D and back to A. I hope that makes sense. This is a very simple definition of how a cycle looks. Okay, so now I'm going to ask a question. Given a graph G, give me an algorithm to check if G has a cycle. So, okay, I'll also give a giveaway. Use what we just learned. Can you not? Yeah. So, any ideas straight off the bat? What we can do? Yeah, I already see answers in the chat. Do you want to unmute and explain, or does anyone else want to? Yeah. All very good ideas, and all of them are correct. Any other ways of saying? Does anyone want to unmute and explain, or should I go on? Okay. So the way all three of the answers which are given by Om, Harshit, and Advik are correct, and they all are actually the same. One second. Can you do this? If we visit visited X. We had done DFS. Oh, yeah, Bhairav, go on. DFS and check if. Yeah, go on.
What if we just have the graph A, B, and C, whereas an edge from A to B, B to C, and A to C?
Okay.
So then we go from we start with A, BFS, we go from A to C, then we go from A to B. Then, then we've already visited C, right? So then we go from B to C, but then C is already visited. So then we declare that as a cycle.
Very good. Very good. So, does everyone see what Bhairav is trying to say here? Okay. So, do you want to tell me how you can fix this?
No, I don't know.
Okay,
But
no problem.
maybe
So, do you think we can use the DFS tree? Anyone else? Does anyone have an answer of how we can fix this seemingly difficult problem? Okay, I'll give everyone a minute to think about this. Yeah, I'll just go on.
So basically, we can just store the previous node that we visited the current node from, and then we iterate over all the neighbors of the current node. And now, if a neighbor is visited but it's not the previous node, then we found the cycle.
Yeah. So, what Advik is correctly saying is that you do this. You say for every node, let me define parent of u. So a parent of a node is the node from which it was first found during the DFS iteration. So if you had something like u to v, then you would say that v is a child and u is a parent. And if you notice what a cycle looks like, it will be something like this. Oh, okay, this is a bad example. And Advik, how will this solve the previous problem? What will be different from this case from what Bhairav said?
So basically, the difference is that when we're visiting from W to U, the difference is that U is not the parent of W, it's not V. The parent of W is actually V. That's why we found the cycle.
Exactly. Exactly. That's a very nice way of explaining it. Because we found V to W, we can say that parent of W is V, is V. And now when we move from W to U, the problem which Bhairav earlier pointed out is not hit again. Does this make sense to everyone? It's a very nice um, understanding of how DFS works. Sure, I can repeat. Yeah. So I'll explain the parent. No, it would not cause a similar problem because now we have a parent to child relation for each node, which is of the form, say, u to v. And then when you have v to w, you already have a parent for that node. The parent is not redefined. In every time we traverse an edge. A parent child is defined at the first point when I visit, say, u, the vertex from which I visited u, that is to say, v. So if I went from v to u, v would be parent and u would be child. And now, when you move from, say, u to w, and then you come back from w to u, you do not say that W is the parent of U. You already have that the parent of U is V. So the same false identification does not happen. Okay, I hope that made sense. Okay, very nice. This is a slightly tricky concept at the first time, as the example Berev pointed out is quite educational. As you can see, why just simply DFS on its own it works, but this parent-child concept is very nice in understanding how you get the child. I'll explain it. So in other words, no node can have two parent side. Exactly. And in the way, the other way in which you can look at it is like this. If you have A to B to C, then you cannot have this. Okay, so I'll just go over the example that was given. You have A to B to C to D, A to E, and E to D, right? You're doing DFS from A, I assume. So you would go A to C, B to C to D, right? And then you would go to E. Sorry, just one second. I'm getting confused myself. Give me a second. Sorry. Uh, yeah, I am very, very sorry. I got a bit confused myself. I'm sorry. I'm so sorry. Just give me a second. I'm trying to figure this out. I've got confused myself. Just give me a second. Yeah, yeah. Okay. Yeah, I'm sorry. So this example, this method which was given would find a cycle in a undirected graph. For finding a cycle in a directed graph, you use something called back edges, which is different. And it's like you need to explain tree edge notation. So let's just keep it for finding cycles in an undirected graph. But for those who are interested, I can explain back edge, front edges, and stuff after the main lecture is over. So, and again, I'm sorry, I just got a bit confused myself. Sorry about that. So yeah, this was a good catch. I'm sorry about that. I got confused. Yeah. So, okay, coming back to what we finished what BFS is and what DFS is. So let's go over another nice problem. So I hope the cycle finding thing is clear. I'm sorry if everyone got confused because of my mistake. Sorry about that. Okay, cool. Okay, cool. Yeah. So, um, okay, clear, clear. Okay, very nice. So now I will be going over the following problem. Some of these problems in the beginning are quite simple. It's just to ensure that we understand how BFS and DFS are used. So given a graph G, okay, I'm not going to write the question. I'm going to write it in a different way. So do you remember the very first graph on which we did BFS, this graph. So when we did BFS on this graph, we got a tree-like structure which covered all of these edges. These edges were not touched at all because our BFS was from S, right? That was the vertex from which we did BFS. But suppose we also wanted the like BFS tree of, sorry, EFGW. Can someone think of what we can do to get this as well? So what we did was BFS from S, which gave us a BFS tree. But now we want EFGW tree structure. So what to do? Okay, so what we can do is just do another BF. Yeah, go on.
Sir, so basically my idea was we start iterating over all the nodes. Now, if any node is not visited in the is not marked as visited, we apply a BFS on it, and then we just move on to the node.
Perfect. I could not have said it better. So, as Advik rightly said, what we do is you go through every possible node, but you do it in a smart way. So you say, like, let's start from the beginning. Let's start from S. Do BFS on S. Very nice. So at the beginning, S, nothing is visited. All vertices are unvisited. So S, we can do BFS on S. BFS on S. So a certain number of vertices will be visited in this process. And in our example, it's everything except these four. So when our iteration goes on, we will hit A, we will hit B, we will hit C. But for all of these, we will have the case that we have visited these already. Since we have visited all of these, we can just skip over them because since they're already visited, they will be a part of the tree structure of BFS of S. So at some point, we will hit one of these four. We have to, since we are iterating over all possible nodes. So when we hit one of these, we just run BFS from that. So you do BFS of E. So when you do BFS of E, you will get its tree-like structure. And suppose there was some node alpha which was left out, then at the end when you would reach alpha, because it's unvisited, you do BFS on alpha, and in this way you cover all possible nodes. So the way you do this is for each node, if not visited, BFS on that node. Right? Quite simple method. Yeah. Does this make sense to everyone? Okay. Now let me just open the problem which I want to cover. Give me a second. Okay. So before we go over some more problems, I'll explain one last, I think, maybe one more after this, but concept, and then we can do just problems. Dijkstra as well. But for BFS and DFS, this is like the amount of theory we will do. I will just define one last term because it's used in a problem, or maybe two terms. It's called a connected component. Connected component. So I'm already clarifying this is for an undirected graph. So there's no confusion. You can define like connected components don't exist for directed graphs. You have something called strongly connected components, but that will be an entire lecture of its own. So just for undirected graphs, just by looking at it, can someone tell me what a connected component would be? What does someone think it would be? Just from the name. Yeah, it is connected. Yeah, it is connected, but how would you define connected? We can go from any one node to every other node belonging to the same component. Exactly. That is a very nice definition from Ramak. Yeah, chess coder, that's also right. Every node is accessible from every other node. Yeah. What it means is that a subset of vertices such that, yes, and it is maximum. Correct. Uh, and it is maximum. Yeah. So let's leave out the maximal part for now. Let's just explain what the basic gist of a connected component is. So you have a subset of vertices such that for every pair of vertices, u comma v of that subset, okay, I'm going to give two options. There is an edge u to v, or you can reach v from u through a path of edges. Which one is correct? Yeah, the second one is correct. Also note that if there is an edge from u to v for all vertices, it is a connected component, but that's not the definition. Like even a path suffices. This would just be a special case of this, right? And this would be a special case where you have like two vertices, right? You can't even have three. Okay, you can have, oh no, you can have, this would be a perfect graph, my bad. This would be a graph where for every two, a perfectly connected component. So I'll just define that as well. So this is a case where you have a PCC, a perfectly connected component. And this is a connected component, right? From here, I can get to here, I can get here, and I can get here. From here, I can get here, here, and here. From here, I can, yeah, I guess you can see the point. From any vertex, you can reach every other vertex. That is correct. It is also known as a click, yeah. But here you can see that there is a path from U, and maybe let's call this V. There's no singular edge from U to V, right? There is a path. You go from here to here, then you go from here to here, and then you go from here to here. But in the case where you had an edge from here to here, an edge from here to here, and an edge from here to here, let's call this W and let's call this X. Do you see how this is this? Yeah. For every two pairs, there's a direct edge from that. So this is also a connected component. This is definitely a connected component, but it's a special case of a connected component, which is better said, it's called a clique or a perfectly connected component. So that's defining what a connected component is. Okay, so now I'm going to ask a question. We've talked about BFS, DFS, and now connected components. Is there some relation? Can anyone see some relation of why I did connected components after BFS and DFS? We use it, yeah. Yeah, we use it, but maybe a bit more elaborate. BFS and DFS identify connected components. Yeah, we can use BFS to find number of components. Yeah, all of these are correct. Traversal, yeah, I guess you mean that we can use the BFS and DFS traversal to find connected components. Yeah. So does everyone see how we can use BFS and DFS to count or cover number of connected components? We kind of did it already, or do you want me to go over it once more? Does anyone see that UFDS? Yeah, chess code UFDS is correct. You can use DSU, but what we actually did, the previous problem, for which we had the algorithm that for every node, if not visited, just do DFS on it. That is the solution to this problem. Does everyone see that? That's a quite nice catch from Advait. Does everyone see that? Because what we did was we tried to find the tree, which is we tried to find everything reachable from S. But that's nothing but the connected component, right? Then once that part is over, we move to another source and then repeat. So we're just finding all the connected components. I'm going to assume that it made sense to everybody. If something does not make sense, please do tell me. Now, we previously did distinction of graphs into directed and undirected, right? Also, guys, yeah, this should be the last theory concept for BFS DFS. After this, it's problems. Don't worry. So we did directed, undirected. There is another distinction which we can make. And this is where I feel graphs get super interesting. I mean, all this is also interesting. It just gets more interesting, I guess. There's something called weighted v unweighted. Yep, exactly. So what this means is that till now, all edges were equal in magnitude per se, because it means that if I can go from U to V and going from V to W, it's like the same for me. The nodes from which the nodes which are connected by the edges are different, but that's about it. Otherwise, both of them are just edges. But now we add, like, you can say, another parameter. We add a weight. Usually, in some cases, the weight parameter is considered as cost or time. Like if I go back to our zombie apocalypse situation, that we can say that from going to Ti to Tj, it takes us some time, say 7 seconds, 7 hours. Was I going to say 7 seconds? Seriously? Okay. And we can say that going from TL to Tm costs us 9 hours. So suppose I have Ti to Tj, and then I have TL to to Tj, let's just say, for simplicity, to Tj. And then which would I prefer? Let's make these undirected. And I want to go to I want to go to J from I or L. Then which would I prefer? Obviously, the one with lesser time, right? I would prefer the one which takes me less time or less cost. So that's where the concept of weighted and unweighted edges come in. I'll explain this a bit more formally. So if G is equal to V comma E, for each edge E belonging to E, we associate a parameter C. We associate a parameter C with the edge E. This is termed as the weight of the edge. I'll just give an example of a quick example of a weighted graph. This is an unweighted graph, weighted graph. For each edge, E to B is an edge, E to C is an edge, I add a weight. Now, suppose I want to find the shortest path in a weighted graph, where shortest, okay, so do you see how in shortest path for undirected graphs, we intuitively define shortest as least number of edges, right? That's the quickest way you get from some I to some J, is how few edges can you traverse to reach that point. Now, is that valid? If I had A to B to C to D to E, and this, say with 10, 1, 1, 1, 1. What would BFS give me the shortest path as? A to E, which costs me 10. But I want the shortest path to be A to B to C to D to E, which just costs me 4. Does this make sense? What I want is not something BFS can give me. Okay. Now I have a very interesting claim. Now this is a very nice thing. So listen carefully because it's quite interesting. So I am saying I can actually use BFS to still solve this problem. Yeah, that would change queue into priority queue set. Okay, we can get to the implementation details in some time, but now I have something to say. Let me erase this. And this is a question I want everyone to think about for a minute because it's a quite interesting question. Let me actually go to the next page. So if I have an edge E equals U comma V with weight C, U to V with weight C, is this not equivalent to having U to some vertex to some vertex to some to V, each of these of cost 1? I think you should have C minus 1. No, you should have C of these. I hope my math is right. Yeah, you should have C of these. Is this not equivalent? If I make, doesn't this imply I can make any weighted graph unweighted? Because every edge of, say, this edge has weight C, I can make it C edges of weight 1. If I have some edge with weight C dash, this is equivalent to C dash edges of weight 1. Does this make sense to everybody? This is equivalent, right? So why am I bringing up this entire concept of weights? Doesn't it seem kind of not necessary? I can just use unweighted graphs algorithm to solve weighted graphs problem. That seems to make my life a lot simpler because now I don't need any new algorithm. I can just do BFS, right? So think about this. So first of all, does everyone agree with me? These two are equivalent. This and this is the same. Yeah, everyone agrees with me. So just use BFS to solve for shortest path, right? For weighted edges as well. Why do I need something else? So does everyone agree with me now? BFS works for weighted graphs as well? You have a weighted graph and then you make it unweighted and you do BFS on it. It works, right? Okay. Can everyone just give me yes or no answers? Does BFS work on a weighted graph which I convert to unweighted? Just yes or no. No, yes or no, not depends. Okay, I see a no. Very interesting. Okay, yes or no. Okay, more people. This is an interesting question. Like all of you should try and think. Just yes or no. What do you think? My question is just, does it work? If I convert a weighted graph into unweighted using this method, will BFS work on it? Okay, guys, no yes and no answers. Just yes or no. Will it work? Yes, with some modification. Yeah, so I'm assuming you mean that the modification is this, right? What I explained here. How you convert. Okay, yes. Yeah. So all the people who said yes and no, or just no, preferably people who said no. Did anyone say no? Yeah. Okay, Advik, you said no. Can you tell me why you think it's no?
Like basically for some cases where the weight may be too high, like 10 to 9, we may have to create too many edges and then even BFS would give a time.
Okay, so interesting. What Advik is saying is that suppose I have U to V with weight. Yeah, exactly. That's what I'm getting to. It would still theoretically work. Yeah. But this is a very good point. So I'm going to explain why people were saying yes and no. Because this is a very nice question in that way. With weight 10 to the power of 9. So what Advik is saying is, if I have to divide this as follows, -1. Wow, I thought of that. To V negative edge weights. Okay, so yeah, in this case, edge weights are not even equal to 0, are greater than 0. We will get to negative edge weights, maybe not this lecture, maybe this lecture. Let's see, I might do a small thing with negative edge weights, but otherwise negative edge weights will come later on. So edge weights are greater than 0. But again, all of these are, this is why I find graphs so nice. There are all these small edge cases which can completely change a problem, because as he's saying, if you have negative edge weights, you can divide this infinitely long. But okay, let's get back to the main question. So our algorithm says, okay, let me form 10 to the power of 9 edges and let me do BFS. So it works. As Avigna said, it works. But Advik's point is, it's memory or computationally too expensive. Integer weights. Okay, so yeah, let's get to all of these edge cases later. Let's keep it simple right now. I should have defined everything, but I was just trying to keep it simple so it does not complicate too much. But does everyone see this? It theoretically works. I can do this modification, that I can convert a weighted graph to unweighted and then use BFS, but it could be memorially or computationally too expensive. Does that make sense? Okay. If it does not make sense, can you raise your hand or message? And if it makes sense also, can you message so I understand? Yeah, exactly. The algo would give the correct answer. It may not even take that much time, because the memory is the real problem. Yeah, but you would have too many operations. You have to break the edge and then build the edge. And yeah. So if there were no constraints, how would the implementation look like? Okay. So so the implementation would look like this. So my input is n and m, which are the number of edges and nodes. This is basically the format we'll always use. N is number of nodes, m is number of edges. And just for simplicity's sake, I'm going to say that my nodes are labeled 1, 2, all the way up to n. Then my next input would be edges. So I would have m lines of input, which is say 1 to 3, 2 to 4, 5 to 6, so on and so forth. But the main thing is each of these have a cost with them, say 7, 3, and 5. Then what the implementation would do is that it would say, okay, 1 to 3 has cost 7. So let me add all of these dummy nodes. Let me make it 1 to A1, to A2, to A3, to A6, right? 1, 2, 3, 4, 5, 6, 7. Yeah, 2, 3. And each of these have weight 1. This is equivalent to this. Then you would have the same thing for 2 to 4, but its cost is 3, so it would do this. 1, okay, and then 2 to 4. So if every edge weight is 1, that's equivalent to not having edge weights at all, right? And then I would just say, okay, do BFS, and then yeah. But as Bera was saying, and as Advik pointed out earlier, what if your cost is 10 to the power of 15? Or 10 to the power of 100? Let's just say, why not? I would have to create 10 to the power of 100 minus 1 new nodes. If you can find a computer which does it for me, well, okay, sure. But do you see the point? That's how the implementation would look. And that's the problem with this implementation. And I hope this paints a picture of the relation between weighted and unweighted So I have not discovered any data type which can hold that, which is why this is not plausible for high values. It's only plausible for cases where we are saying there are five nodes and three edges and cost is like less than five and stuff like that. When we're just it just this is a theoretical thing which just explains the conversion from a weighted to an unweighted graph. I hope this made sense. Okay, I don't even know what big integer in Java is, but if it can hold 10 to the 100, you'd still have a problem because you're creating 10 to the power of 100 nodes. Like, come on. Okay, so if all of this is clear, I'm actually going to give everyone 2 to 3 minutes here. Can you think of any algorithm to solve the shortest path by cost in a directed and weighted graph? All weights are not same. All weights are not the same. Also, everything I said before, everything is positive, all that still holds. So I'm going to give you guys 2 to 3 minutes. Okay. I don't even know what Dijkstra is. So you'll have to explain it to me. So, okay, maybe 2 to 3 minutes for everyone who's not seen the algorithm before. You can think about it. Yeah, I'll also think about it. Yeah, 2 or 3 minutes, or maybe even 5 minutes. Okay. Okay, the answer is yes. The next question is, what is this algorithm? Yeah, well, sorry, I'm not in the mood of being fair at this moment. Okay, so guys, what have you thought? If someone tells me Dijkstra, uh, I don't know what to say. Okay, if someone tells me Dijkstra, they have to explain what Dijkstra is with proof, why it doesn't work, everything you know about Dijkstra. You know what? People might actually be able to do that. That's probably not the best thing I can say. Uh, okay, Avigna, you think it's fair? Okay, sure. So if someone answers this is Dijkstra, you have to answer That's how I pronounce it. I don't know how it's pronounced. So yeah, what have people thought about? Guys, come on. Surely someone has thought of something. I wholeheartedly agree with Avigna. I mean, if you guys want me to call it a day, then we won't get to do problems because I'll cover Dijkstra and then I can do problems as well. Yeah. Okay. Here we go, Advik. Take the node with minimum distance that's to be explored. Source has 0 initially. For all neighbors, check whether the distance of reaching the neighbor, the current node, is lesser than the distance stored in the neighbor. If so, then update the distance and okay. So I don't know if it's correct or not. So Advik, can you give us a logical argument for why you think this is correct? Yeah.
So basically, what we're guaranteeing that is that we will visit a node only if only the node which has the minimum distance to be visited. So we visit the node with the minimum distance that's to be explored first. So basically, we always visit the node that is at the closest distance first, and then using this, we add the rest of the nodes. So it's guaranteed that we will find the shortest path.
That sounds good to me. You're picking the node. Yeah, okay. Does anyone else disagree with his argument? Okay, very nice. So I am just going to write pseudocode quickly for this. Uh, here. Yeah. So I think there's a chat message. Yeah. This is not dealing with negative edge weights. We're not dealing with negative edge weights. So yeah, I had a interesting implementation which I wrote down. Let me just pull that up. Where did I? Yeah, here. Here, yeah. So I'm going to say that, yeah. Now, okay, there's no need right now. Let S be the source. So then distance of S is equal to 0. And let the set capital S equal to the null set. Then while the chat message. Yes, for negative edge weights, you do use Bellman-Ford. You can use Bellman-Ford at least, but I don't think we'll be covering that today. We're a bit time bound, sadly. Yeah. And S is not equal to V. What we will do is, okay, what Advik said. U is the vertex, the smallest. B value S equal to S union U. This is union, this is U, by the way. I hope that's clear. Now, after this is done, for each vertex neighborhood view. Any ideas? Now what? I know this was explained orally, but any mathematical way of writing it? Does anyone have? Or okay, you know what? Let me write it. If D of is greater than rate of UV, then DF. Right? If it's greater than the edge weight, then you just change it and then you move on. Does this make sense to everybody? Okay. 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 Is there anyone who doesn't agree with this? Okay, there is a small error in this. Can someone find out what the error is? Okay, this much is correct. This much is correct. WUV is just weight of the edge from U2. DV is greater than. Oh wait, okay, that was sorry. I got confused in my own handwriting of U's and V's. Okay, that could have been the mistake. Yeah, that could have been something else. I am definitely not saying that there's nothing else. So I don't know now. Whatever you will say, I will change. So let's hope what you are saying is right. I'm going to change it. So tell me now. Does this seem correct now? You guys will have to decide. Okay, we have one more idea here. Okay, I'm going to write these all down as options, and then you can decide which is correct. I have D of V is greater than weight of UV plus D, what? Yeah, U, and then dV equals weight of UV plus du. This is another option. This seems overly complicated to me, that you just want the minimum distance node, right? Why would I need this? This handles it efficiently for me, right? What does everyone think? Is option number 1 correct or is option number 2 correct? Don't say 2 just because it looks more complicated. One follows the idea which we were moving forward with, right? At every point, you try to find the minimum distance node and then you union it to your discovered set. Okay. Advik is convinced it's 2, but does anyone think it's 1? Does anyone think it's something else? Okay, yeah, we have 1. Keep it simple, guys. Keep it simple. Any other answers? Okay, we have people saying 1 and 2. I'll wait for one more answer and then ask people to explain that choice. I guess that might be productive. Also, Ramak, I don't know if your answer is correct or not, but what do you mean by recursion? There is, like, if we were doing recursion, it would be something of the form du is equal to, you do something with du minus k, and then you do something with that, where you're using something previously built and then calling that value. This isn't really recursion. What Advik is saying, I'm not quite sure what he's saying, but he seems to be saying that if you have some node, you have to consider everything before it. That's something like what he's trying to say. Yeah, we have some people saying 2 as well. Okay, so someone who said 1. Can you explain your reasoning? Who said 1? Yamunan, go on. Okay, then maybe we can have someone who says 2. Okay, it just seemed intuitive. Yeah, it seems simple, but some people seem fixated on the fact that it's 2. So, Harshit, you can explain why you think it's option number 2. Oh, yeah, after him, you cannot pick. You can feel free to unmute, or if that doesn't work, okay. You're saying we have to we have to consider the previous nodes. But why do you have to consider the previous nodes? What we said was, from some node you just have to find the minimum to the next one, right? Okay, I think Advik is dying to answer. Yeah, go on.
So basically, the distance till U is the minimum distance through any path. Now, if I wanted to reach V, I would add the edge because the path originally decided for U. I'm just adding the edge WUV. That's why the original cost of the path plus the cost of WUV should be the cost I'm trying for DV.
Okay, that made sense to me. So now you all tell me. After Advik's explanation, do you want to go with one or two? Both make sense to me. I'm sorry, my brain is not working. Tell me one or two. I will go with whatever you say. Are people convinced with Advik's argument, or do you still think it's one? You tell me, Om. Do you think it's number one or number two? If you say one, I'll ask you to explain why it's one. If you say two, I'll ask you to explain why it's two. So, yeah. Okay, enough suspense. The answer is indeed number two. This is the correct answer. So, yeah. But this was quite productive. I think a lot of people thought about why exactly it should be two. And I think Advik's answer was exactly correct. And I'll explain it using a small diagram. So, what he was saying is that if you're at some node P, you already have some. Okay, so this is the part of set S, and this is the part of V minus S. Does that make sense? Because you had S, which was a set, and we are doing this till while S is not equal to V. So I'll explain why it's this and not this. So what actually we're doing is that we would have had some path from U to P, which is already created. And then we're looking for the next vertex from all of these, which have to be added. Well, you cannot just look at this distance, because the minimum weight, the minimum distance of these can still be different from whatever this path is. Advik explained it really well, saying that it's not just the last node you have to consider, which you're bringing into the set. You have to consider that you want to find the shortest path in general. So you have to consider the entire path, and if that with an added vertex makes it shorter or not. And only if it does, then do you change it. The greater than sign case means that what you already had was more optimum, so you don't have to change anything. But in case it was lesser, then you would be changing your dv, which is distance of v, to this value. Does that make sense? I hope that made sense. This is yeah, I'm not saying anything. I'm waiting to see if everyone has understood or not in general. Okay, getting a lot of thumbs up. That's nice. Okay, then I'll just assume that all of this is clear. So, what all did we cover today? We covered BFS, DFS, Dijkstra, then weighted versus unweighted, directed versus undirected, cycle detection, and we also discussed one more thing, right? Yeah, connected components. Am I on? Okay, connected components. In this much, does anyone have any questions? Except generalization of cycle detection, because that is like, I can do it now, but it's just, I feel it's not required like at this point, just for graphs, one BFS, DFS, and Dijkstra should be enough. Yeah, go on.
What is the proof for Dijkstra's algorithm?
Okay, I can go over the proof now, but uh, I can attach it as a lecture guide as well, because I feel that there's a very nice proof which I read once. It explains it very nicely with diagrams, and my diagram drawing skill is kind of terrible. So I feel like it might be better for all of you to do it at your own pace. So I'll just attach it as a guide if that's okay.
Okay, thank you.
Yeah. Is there
And
any? Yeah.
also the analysis of Dijkstra. Will
What?
that be attached?
Like a
The
run?
analysis for Dijkstra's algorithm.
Do you mean runtime analysis or like?
Yes, yes.
Okay. So just a question, Avigna, have you done asymptotic notation? So I don't know how else I can do runtime. Have you done asymptotic notation? Yeah, no, I'm not asking if you know it. I'm asking if it has been covered in. No, like Naveen, it just means like O of n plus m, all that stuff. Yeah, big O time complexity. Have you covered that? Or no? It's just called asymptotic notation. Okay, if people know it, then uh, yeah, exactly. Okay, I am myself a bit rusty with the runtime of Dijkstra, so we'll have to work through it together. I can go over BFS and DFS. Those are. Sorry, what? Oh, what do you mean, Avigna? I didn't get. What do you mean? I I think it's like not relevant. But okay, what I can do is just give a brief overview of what runtime is, and then maybe you can see the proofs yourself if that's easier. So I'm just going to define what big O time complexity is, since people want to learn it. So sure, why not? So let's consider this graph where you have three functions f of x, g of x, and h of x, and you have some constant c on this axis. So say c is here. So you have some f of x, some, okay, now this is not the right word. Something like this, something like this, and then something like this. And this is my c. Okay. Yeah, n plus m log n. I mean, isn't it of m log n with best case implementation? Yeah, m log n. I don't think it's n plus m. Yeah, you visit each node once, so it's actually m log n. But we'll go over it after. Yeah, and the log factors prior to q. Yeah, we can go over that. Okay, we'll go over that. Let me just finish what big O is for people who've not seen it before, and then we can go into this. So basically what it means is that if you consider this point C, let this point be C. So after point C, so after f of C, g of C, C, and h of C, you can see that if this is f, this is g, maybe I'll use colors, that might make it easier. So if this is f, if this is g, and this is h, then you see that after point C, g of x is upper bounded by f of x. Just we're assuming that this happens. That after this point C, g of x is upper bounded by f of x. Then what we say is that f of x is equal to big O of g of x. Big O basically means upper bound, omega means lower bound, and theta means tight bound, but those are not like the only one which we use in competitive programming is big omega. big O, sorry. So big O just basically means upper bound. So now let me explain this in a different way. So let me give a code snippet real quick. So for I in range n, for j in range I, do whatever you want. So if you look at this code snippet, we can see that this loop will run at most n times. Now this one will clearly run less than n times, but we can upper bound it by n times, because that's what our function definition is. We're saying that after this point c, f of x is always going to be greater than equal to g of x for all possible values. So f of x is an upper bound of g of x. So in this case, you can say that n squared is an upper bound on the number of iterations of this snippet, right? Thus, we say the runtime of this is O of n squared. That means in the worst case, it's going to be n squared, asymptotically n squared. Now, since we're doing asymptotic notation, I'll add some cool points that in asymptotic notation, if you have stuff like O is equal to O of n squared plus like 2, or if you have O of 2n squared, all of these constant values can just be dropped, because asymptotically, if you consider the function, 2 grows extremely slowly as compared to n squared. 2 is a constant, and 2 also, like this multiplication by 2, it grows extremely slowly in comparison with like n squared. If you had, for example, n squared plus n cubed, then obviously you cannot drop the n cubed value. In this case, you drop n squared. So this is all just an explanation of how asymptotic notation works on a whole. And with this, you can find runtime of algorithms. So let's just go over something. Should we go over one more code snippet, or should I go straight into BFS DFS? Guys, which case do you want? Okay, I don't know. I'll give one more code snippet if people want. But yeah, one more. Sure. Yeah. Okay. Cool. So let's see what code snippet can I. Okay. So, oh, I have a very nice code snippet. Okay, this is a very nice code snippet. So let's call this code snippet power of 2 calculation, where I'm going to say that P of n is 2 to the power of n. And I am going to define P of n as, let me just remember how it was defined. P of n minus 1, n minus 1, yeah, plus P of n minus 1. And my base case is that if n is equal to 0, return 1. Let's do this. Can someone tell me what will be, okay, I'm actually going to give, yeah. What will be the runtime of this code snippet? Okay, Naveen, yeah, 2 to the n, yeah, right. Because what you're actually doing is, this is basically a, yeah, it's okay. Yeah, what you're doing is that if you want to calculate, say, P of 5, what you're going to do is divide this as P of 4 and P of 4. And then here you would go P of 3, P of 3. Here you'd also go P of 3, P of 3. I think Naveen kind of covered this in his DP lecture, where he was saying that this is a bad way of, computing something like this. Yeah, in the Fibonacci problem. Exactly like the Fibonacci problem. You would instead save all these values and improve your runtime because of that. So, but did everyone see how this is 2 to the n? Because if you have P to the n, you're just going to go P to the n minus 1 and P to the n minus 1. And then you're just going to have a complete binary tree, because each node will have 2 children. So this would just be 2 to the n. because the height of the tree would be n. So does this like runtime make sense? Yeah, I'm just gonna assume it makes sense. Because yeah. So runtime of BFS now. Runtime of DFS might be simpler. Yeah, Fibonacci and 2 to the n bad recursive algorithms are standard examples. Yes. So runtime of DFS. How do I explain this? Okay. So when we are doing DFS on some source node, do you notice, yes, O of n plus m, that what we are doing is a traversal. And whenever you are traversing, you have n nodes to traverse, and you have m edges to traverse. So what you end up doing is your algorithm will cover all the edges. So now we're talking in big O notation. So big O of all the edges. It will, in the worst case, cover all the edges, and in the worst case, cover all the nodes. So that would just be O of n plus m. Now, the reason this is plus is because what we are doing is not nested. We're not doing for each node you do DFS. It's not like that. If you had for each node you do DFS, okay, so it's just someone can answer this. If you have an algorithm where you're running DFS n times, what would your runtime be given that this is your runtime for one DFS iteration? Any answers? Oh, it's the chat. Any answers? Okay, I'll just, maybe I didn't clarify the question. You run DFS n times. What's your runtime? Yeah, exactly. It's O of n times n plus m, which is O of n squared plus m, which is equal to O of n squared. So if you run DFS n times, it's going to be n squared. So the runtime analysis for BFS and DFS is quite straightforward because you're just traversing all the edges and nodes. So it's just going to be n plus m for both cases. For, okay, Naveen, do you not agree? Did I say something wrong? Oh, sorry. My math is, sorry. Okay, this would be n squared plus nm. And if it's n squared plus nm, and if n and m are small, you can drop it, but let's just keep n and m for now. Naveen, which case are you talking about? O of n plus m for visited array for what? Oh, okay. You're saying that for this case, you can do it in O of n plus m to find connected components. Okay. So Naveen is talking about a slightly different case from what we're saying. He's talking about this algorithm. For each node, if not visited, do DFS. That's the algorithm he's talking about. And that would be O of n plus m. And this is our algorithm to find connected components. The algorithm which I was saying is hypothetically, if you have n nodes and you run DFS from all of them, DFS from 1, DFS from 2, all the way up to DFS from n. I don't even know where this is used, but in case this was just to show how it would be O of n times n plus m because it's nested. For all the nodes, you're doing n plus m times, so it's n squared plus nm. But in one DFS iteration, you're just doing one iteration, so it's just n plus m. That's what I was trying to explain, why it's plus and not multiplication. So yeah, this covers the basics of runtime analysis. And I think it's almost 10. So maybe we should stop for today. And the problem set for BFS, DFS, and Dijkstra, I would suggest, okay, yeah, I have the problems written down. Let me just open them and send the links. For people who are just starting with graph algorithms, I would suggest the following problems. I'm sending it in the chat. Uh, where's the third problem I had? Yeah. Okay, the flight routes. Yeah, flight routes. And there was one more. Yeah, and this. These are the 4 problems which I would suggest as a basic start to BFS, DFS, and Dijkstra, and all the concepts which we covered today. A problem set which is harder, which would include implicit graphs, which is like seeing a situation and figuring out how you would convert it into a graph and solving the problem. I'll send that problem set a bit later along with the notes for this lecture. I hope that's okay. Maybe after everyone has tried all the problems, we can have a discussion session for those. I'm okay with that. Okay, if you've done all of them, that's great. I will send you it'll be on the spoil lectures thing, the harder set, which is like, these are just basics. If you're doing BFS, DFS, and Dijkstra for the first time, I would suggest doing these problems. Naveen or Avigna, if you know any other basic problems, you can just add it here. But I feel this covers BFS, DFS, and Dijkstra. So yeah, that was what we planned for today. And I will send the proof of Dijkstra along with its runtime analysis and add it to the lecture notes. And as Naveen is saying, you can always go to Code Forces and try 3500 rated problems. If you don't get them, do ask Naveen for the solution. I'm pretty sure he will have all of them with explanation. How does that sound? Discussion of back edges, I mean, it's already 10, that's the problem. But again, I can send it as notes. So cycle detection for directed graphs, I can also add that. Sure. I will add that. I hope everyone enjoyed and understood graphs a bit better. Also, we'll be sending out a feedback form for how the lecture was. So do tell me how I could have improved. That will help me a lot. So thank you guys. Thank you so much, everyone. Thank you. Vigna, I guess you can end the recording, or should I just end the meet? I don't know. Should I end the meeting?